this talk. And we start with Alejandro from the Universidade de Lógica. We will be talking about polynomial theoretical basis for a general senior computer based on polynomials. So, Alejandro.
Thank you very much. Thanks for coming. So, as Rafael said, my name is Alejandro. I am a first year master student from the Universidad de Antioquia. I'm from Medellin, Colombia. And the idea of this talk is presenting some theoretical concepts that we need to take into account if we want to solve some logical problems, but in a computing way, okay? And we will use polynomials, okay? The talk will be divided in 5 sections. The first one, we are going to talk a little bit about the motivation of this problem. In the second and the third one, we are going to introduce the concepts that we need from the logic world and the concepts that we need from the algebraic world, okay? The fourth section is basically how can we link logic with algebraic regarding polynomials. And the last one is talking about how can we translate some logical problems like deduction, satisfiability, finding a model in a problem about or regarding the solution of systems equations or other characteristics of polynomials. Right? So let's start. Following Xian in a paper of 1985, we can trace back the idea of using algebra to solve logical problems from the Stone isomorphism. So in this paper, Xian used the Stone isomorphism between Boolean algebras and Boolean rings to tackle some logical problems. And the idea is like kind of simple if you know something about category theory. Basically what we are going to do here is going from the category of logic to the category of algebra of polynomials and then solve the problem in the world of algebra. And if we have a way to come back, we can recover the solution of the logical problem, okay? In this way, at the end, the problem will be to solve the algebraic problems. So, in these matters, we have an expert here, which is the Professor Carnielli. Okay, so we have basically 2 approaches. Polynomial ring calculus, being the founder, the Professor Carnielli, and we have another approach which is related to the theory of group knot bases. Okay, the first one to propose this approach was Cesaraini, Alonso, Briales, and then applied by the rest of the authors. Okay, using different logical systems. So let's introduce what we need. Okay, you know that there are many different logical systems, but we are going to tackle in a subgroup or in a subset of these logical systems. So remember that to define a logical system, we need 2 things: a set of well-formed formulas and a consequence relationship. This is pretty standard. To define a set of well-formed formulas, you just need connectives, each one with its own arity, and we need a set of propositional variables, okay? And we can define the set of well-formed formulas inductively, being the base step, the propositional variables and the connectives with arity 0. And then the inductive step is just if we have a connective with arity m distinct to 0, then the application of this connective to a group of formulas, it's also in the set of well-formed formulas, okay? And in the last step, we need to define what would be a consequence relation. In the Tarskian sense, a consequence relation should satisfy or must satisfy 3 conditions: reflexivity, monotonicity, and color. Of course, not all the logical systems satisfy these three conditions. So for example, we do not consider logics such as non-monotonic logics, okay? And finally, so we have the pair is the system of propositional logic, okay? Consequence relation and the set of orders, right? So right now, what it's only missing is the algebraic part, okay, and the link between the logic and the algebraic part. So let's start with the algebraic part, right? So the basis of this is the concept of a ring. It's really simple. It's just a set with two operations, okay, addition and multiplication, and the concept of ring satisfies three conditions. It's an abelian group under addition, it's a monoid under multiplication, and we have the distribution law between multiplication and addition, right? And one specific class of rings are the fields. And the fields are really interesting. Why? Because in the fields we have a commutative, that the multiplication is commutative, and we have multiplicative inverses, right? And remember that similar that we do with vector spaces, we have here a finite field, okay? So we will define a finite field. It's just a field with a finite number of numbers, right? But there is an interesting property from algebra, that is that every finite field is a size, its size is a power of a prime, okay? And we need to take this into consideration when we are translating logic to algebra, okay? So we are not interested in the field itself, but in the size of the field, right? So we will denote all the fields of size q by fq. Once we have the field, we can introduce the concept of polynomial in one variable or in multiple variables. And the idea is basically to generalize to multiple variable polynomials from the one single variable, okay? So basically, when we have multiple variables, we can extend the definition of a monomial defining this formal product, okay? We will denote the set of all monomials by m raised to n, and similar that we have in a polynomial subsingle variable, we can define a kind of order when we consider multiple variables. Basically, we just need two conditions. The first one is a minimal element, and the second one is that the order is preserved under cancellation, okay? One example of this monomial order could be the lexicographic order, when we basically are going to evaluate in the first variable and then move to the second one and the third, okay? And so on. And finally, just a polynomial in n variables can be defined as a linear combination of some coefficients in a ring R. That's why the concept of ring is important here, and the monomials, right? So the idea is basically that when we are talking about these coefficients in R, this keeping the monomials with these coefficients tends or inspires the creation of what we call the ring of polynomials, okay? Which is basically take the polynomials as a set and take into consideration the addition and the multiplicative operations inherited from the original ring, right? Okay. So, until here, basically we have the concepts from the logic and the concepts from polynomials. However, as our main goal is to solve algebraically the problems about polynomials, we need to define some other concepts, okay, in the world of algebra. And the first one is, what is a variety, okay? So if you have a set of polynomials and a subset of the ring, you can define the variety as all the tuples that cancel or vanishes all the polynomials that you consider, right? To simplify the notation, if this subset A is equal to the ring, we can just express the variety in this way. Okay? And with the variety comes the idea of the idea. Okay? So if we have a subset of tuples, we can define the ideal generated by or defined by this subset of tuples as all the polynomials who vanishes in all the elements of B. Okay? And taking this into consideration, we can create polynomials that vanishes at all the points of our subset A of the ring, which what we call auxiliary polynomials. And this will be really important because our main tool in the algebraic world to solve problems regarding polynomials is the Nullstellensatz for finite fields. Okay? And what is saying this theorem basically is that you can calculate the ideal of a variety as the original idea J plus the ideal generated by the auxiliary polynomials, taking into consideration this set A. Why is important when we are distinguishing between this set A? Because, as we mentioned before, all finite fields are of size a power of a prime. However, not all multivalued logics are exactly or has exactly a power of a prime as a number of possible true values. However, with this theorem, we are not worried about that because we just have to find the smallest field that includes all the sets of possible true values. Okay, that's why it's really important, this theorem. Okay, and there is a weak version which is called the weak Nullstellensatz for finite fields, and basically if the variety is empty, then the ideal is all the field of polynomials, right? So right now what we are going to see is how to link these two worlds. Okay, because I think this is the purpose of defining or tackling the problems using algebra. Okay, so let's see. What is missing is what is a consequence relation when we are talking about polynomials. We can define translation from formulas in the logic. We will see that later, to polynomials in the algebra. But remember that we need two things to have a logical system. The set of formulas, we can think that as a check, and the consequence relationship. But in polynomials, we don't have a consequence relationship. However, we can define a consequence relationship, which will be equivalent to the consequence relation in the logic. Okay? So a consequence relation on polynomials based on a subset A of the ring, we will define it in this way. We will say that a group of polynomials deduct in a polynomial way a polynomial f if and only if f vanishes on the variety defined by this group of polynomials restricted to this subset of the ring. Okay? And the main result here is to define how can we characterize a logical system using polynomials. And basically, we need the translation function from the set of Wolfram formulas to polynomials. Okay? This translation function will depend on the system of logic that we consider. So we will assume that we have the translation function. Okay? So at the end, considering this definition of a consequence relationship, we can say that a logic is characterized by polynomials if in every case gamma deduct phi, if and only if the translation of each member of gamma can deduct the translation of phi. Okay? When this translation depends on the subset D of A, which usually is associated with the designated true values. Okay? So this is like the main definition here. So the question now is, okay, some examples, right? So as Carnielli and Agudelo has shown, every finite value logic is characterized by polynomials. So for example, we have classical propositional logic. We can characterize classical propositional logic by polynomials in C2, okay? And we can go further and consider, for example, this paraconsistent logic that we have been talking about since the first day, LFI1, and this logic is characterized in C3, okay? However, not every propositional logic is characterized using a finite valued matrix, okay? But in these cases, the Professor Carnielli and other authors have solved the problem, okay? For example, if we are talking about paraconsistent logics MBC or C1, we can characterize them with polynomials, taking into account the idea of the Professor Carnielli of using the concept of hidden variables, okay?
Adding extra variables.
Exactly. When we add this concept, when in the translation functions, we are able to characterize MBC and C1 through polynomials in C2. And we can go even further to modal logics, okay? So again, the Professor Carnielli and Agudelo has worked in this issue and have shown that S5, K, KD, T, and S4 can be characterized using polynomials, okay? So the last section will be discussing about, okay, we have the translation. What we need is how to solve the algebraic problem, okay? So in this regard, we are going to consider these four observations, okay? We will have a propositional logic, which is characterized by polynomials, and we have a translation in the terms, right? And this logic has a set of possible true values and the set of designated true values, okay? We will simplify the notation, okay, in this regard, and the same applies here with the ideal generated by auxiliary polynomials, okay? And at the end, for Grubner bases, we need a monomial order. In this case, we will consider the lexicographic order, okay? So the thing is, how can we characterize the logical problems in terms of polynomial equations? And that's why Grubner bases become the key idea. Why? Because you can understand Grubner bases as when you have a basis in a vector space, okay? It's just a basis with certain properties that makes the calculations easier, okay? So very briefly, a system of polynomial equations is just a system when we are trying to find a solution that satisfies or vanishes all the polynomials at the same time. A Grubner basis, as I said before, you can understand this as orthonormal space basis when we are talking about vector spaces, okay? So it's like kind of the same idea. It's just a basis with some desirable properties that we need, right? And we call like kind of a reduced form of this Grubner basis. And basically it's just a basis when if an element belongs to this ideal, the leading monomial of the basis of an element of the basis divides the leading monomial of it, okay? And why is Grubner basis key to solve algebraic problems? Thanks to the Buchberger algorithm, okay? Because the Buchberger algorithm reduces all the algebraic problems regarding polynomial systems of equations to see or to work with the Grubner basis, which are really easy to work with, okay? Which kind of problems can we solve with this Buchberger algorithm? Basically four, okay? Determine ideal membership, I mean if a polynomial belongs to an ideal, reduce polynomials to normal forms, these make the calculations easy in the world of polynomials, determine if a system polynomial equations have solution or not, and find solutions to polynomial equations. We have an algorithm proposed by the Professor Agudelo, okay? Okay, perfect. So let's talk about the logical problems. So the first one could be deduction problem. We have a set of formulas and we want to know if the set of formulas can deduct a formula phi, taking into consideration the Grubner basis. At the characterization of the logic using polynomials, this problem is reduced to evaluate if the translation of phi belongs to the ideal generated by gamma, which is basically this one. Okay, so we just have to divide polynomials and see if the reduced Grubner basis has a remainder of 0. Okay, there are some examples. I am not getting to details right now because I am more interested in presenting the dual problem. Okay, satisfiability is related with verifying that the set of the models of gamma is empty or not. But if we take into consideration the Borchberger algorithm, that reduces to find if the system of polynomial equations associated with gamma has a solution or not. Okay. There are also some examples with LFI1. Finding a model. So finding a model is basically finding a solution. Okay. So if we find a solution, we can find a model just extending the concept of the evaluation.
Or counter model.
Exactly. Yeah, exactly. That is the next one. Okay. We just take into account that, remember, this designated true value. So for models, we take the designated true values, but when we are talking about counter model, we can take the complement, right? And finally, we have the tautology and the contradiction problem. But remember that tautology problem is just a particular case of the deduction problem, and the contradiction problem is a particular case of the satisfiability problem. Okay? And that's it. What's next? Because none of these ideas, like I knew or original, but what we are talking is we have two options. The first one is to program the prover. We know that this method works from many different types of logical systems. So we can develop a theorem prover for this system at this, using these techniques and taking into account that from the algebraic part we have some libraries that already done the calculation of Grubner basis and the solution of the algebraic problems. Okay? And the second approach is formalizing some of these results using type theory. Okay, and that's it.
Okay, thank you very much, Alejandro. Andrew?
It's really interesting. Just an idea. I would do it in Mathematica because that has all the procedures for algebra in there. And it's so easy to manipulate formulas into a very efficient code. Instead of doing it, I'm just stuff like this myself. That's just a recommendation. And then it would be easy to use because you can use whatever notation you want.
Yeah, of course.
You would have to trade. It would just be easy to do everything the same.
Okay.
I love the project.
Thank you. Thank you.
Can I say congratulations? It's an excellent work. Your professor of that was my
Yeah, I know.
very bright, very good student. And you guys, you solved the problem. It's very interesting. For 80 years I tried to connect this polynomial with this Nuisance Hilbert problem. And they did it. And they don't, not only they did it, but they used this Borchberger algorithm, Grubner basis. And this is very much interesting. It makes a new bridge between logic and algebraic geometry.
Exactly.
Right? So
Yeah, right.
now you have a bridge connecting logic and algebraic geometry. Because everything can be done like a surface. It's just like a working with the kind of abstract geometry, right?
Exactly.
And it's very natural.
Thank you. Thank you.
Mike?
Okay. So congratulations, because very interesting talk. You were talking about polynomials and vector space that are related to.
No, it's just an idea to explain, because most of the time the people understand more vector space.
Okay. I was, when you talked about bench, polynomials and benches, Does this lead to any relation to Jordan-Cannon forms or anything related to partitioning the space or anything like that?
No, but the algorithm to get a Grubner basis is in a similar way to the Jordan algorithm to take orthonormal space basis.
Okay.
But yeah, if you
Generalizing form.
exactly, it's a generalized.
But if you wanted to see it that way, you can just take reducible polynomials and use reticles to fix that.
Okay.
But yeah, if you are interested, I can tell you the paper when the algorithm where the algorithm is described to get a Grubner basis.
Okay.
Okay, thank you.
Okay, now Miguel is behind all the technology, cameras, and everything, all that very well. And we will present obtaining partial system model logics by means of combinations of logics. Miguel is supervised by Juliano Bueno, who's not here, but he was.
Sorry, not be able to do this.
Yeah.
Now I think at this time.
He's doing master's degree in philosophy here at Unicamp. So, yeah.
Thank you, Rafael. So, this is the theme for my, mainly the project actually, for my master thesis. So this is really ongoing work. So if you find it is a bit early on, that's why. So here's a brief overview of what I'm going to talk about. First, I'll give an introduction to the theme, then I'll talk about the basics of my of what I talk about, then combined logics, cathodic logics, then some conclusions, and finally some references. So, introduction. So, modal logics and bar-consistent logics are well established in basic level, philosophy, mathematics, computer science, and it's not hard to imagine problems that would be useful to be dealt with both modality and consistency or inconsistency. Just this week we saw some applications from Rafael, mainly presented on Monday, that is a modal bar-consistent logic that is used to solve some specific problems. Those show up really fairly frequently. And as such, it is rather natural to a question rather natural arises. Is there is it possible to combine in some algorithmic way modal logics and bar-consistent logics into a single unified logical system? Well, there are many attempts to solve this question, and the attempts that I'm going to focus is on these 3 works by Juliana Bueno, which is my advisor. In these works, she proposed 2 families of logics, those being the anodic logics and the cathodic logics. In her presentation Monday, I believe she mentioned those logics. The anodic logics are strictly positive modal logics, that is, they have no negation nor bottom particle. And the cathodic logics are consistent modal logics, that is, they are the result of combining the anodic logics with some par-consistent logics. These logics were defined in a, let's say, manual way, that is, she defined them from the ground up, defined their language, defined their syntax, defined their semantics, by basically picking and choosing components from both base logics. And relevant properties, those being soundness and completeness, were proven by hand. That is, she didn't get the proofs by some method, she just made it, proved them from the ground up once again. Doing it this way, combining logics this way, thus is not entirely negative. It allows you to analyze really thoroughly what the logics that you're working with, but it is quite cumbersome. It's not easy at all. As such, my work proposes to extend the results that she obtained by showing that it is possible to obtain both new and pre-existing cathodic logics by means of combining the anodic logics with par-consistent logics by means of the method of algebraic firing. So, the basics. First, what makes up a logic? All logics that are relevant for this work are made of, have three components: the signature, the syntactical consequence system, and semantical consequence system. I suppose everyone here knows what the latter two are. I also don't have time to explain those. We're just going to talk briefly about what is a signature, because I found that not every logic textbook goes into detail of what this is. So, the signature of a logic is a set of symbols that represent the connectives of that logic. If a connective can be defined by means of other connectives in that signature, then it need not be present in the signature. By that I mean, say, for example, if you have both negation and conjunction on your signature, you don't need a disjunction, because disjunction can be defined by means of negation conjunction. And the signature of a logic is, the language of a logic is inductively defined over the signature by the usual way, and the signature defines the semantical and syntactical roles of a logic. Here are some amazing examples of signatures. This one on the top, and just the only one I'm going to go into detail. This is the signature of the anodic logic. It has both necessity, possibility, implication, and conjunction. So the anodic logics and the par-consistent logics. The anodic logics, as I said, are strictly positive modal logics. Their signature is that one that I just showed. And due to the fact that they don't have negation or bottom, the modalities, necessity and possibility, cannot be defined in terms of one another. So the logic is strictly bimodal. They are semantically and syntactically defined like any other modal logic, except that they have some actions that explicitly relate necessity and possibility. It's an explicitly related duality between them. Par-consistent logics are logics that don't respect explosion. The signature has a negation that is weaker than the class 1 negation, because it does not have explosion. This negation is usually known as weak negation. The par-consistent logics that are relevant for this work are PI, MBC, BC, and CI. Of these, and the latter three are LFIs also, and the first one is only a usual par-consistent logic that is not an LFI. The LFIs have a consistent operation to internalize the notion of a consistent formula in their language, and deductive explosion can only occur if you have contradiction of consistent formulas. These logics can be semantically defined by relations, usually by relations, and Hilbert's calculus if a weaker explosion rule that represents this notion. So, combining logics. To combine logics is to create a new logical system based on other logics, given some other logics. So, and to do so using a method is to use some kind of algorithm to combine to join up two or more logics into a new logic. This process essentially basically consists of analyzing the components of the logics being combined, combining each component individually, and then joining up the components into this new logic that you are interested in. Each method of combination has its own peculiarities and powers, let's say. So, for example, fusion is a method that is basically the simplest method possible, but is also the most restrictive because it only works on modal logics. And algebraic firing is perhaps the most powerful method, but is also extremely complex. Not extremely, it's very complex. So, combinations of logics can be seen as a method for joining up logics that represent distinctive forms of reasoning in a homogeneous setting. So, this then allows us for the formulation of arguments that contain that are mixed arguments that involve distinctive forms of reasoning, which is a thing that is quite common in philosophy. At least I think it is. I'm not a philosopher. To combine methods without a method then requires the definition of all components of this new logic, together with proofs that of all relevant properties are valid. So I need to define the new language, a new syntax, and new semantics. I need to prove, once again, soundness, I need to prove completeness, prove everything else that I want. And this is not without effort. Whereas combining logics with a method has the benefit of giving us almost immediately all these components, and also ensuring that certain properties that are relevant for us are preserved by the method. So that this means that when I combine logics with a method, say algebraic firing, I know that if these logics respect some basic restrictions, then the resulting logic will respect the properties of both basic logics respected. So, for example, if both basic logics are sound, then so will be the resulting logic. So, how do you combine logics? Well, the method combination utilizes algebraic firing, which is described in the book by Carnielli and Cunilho in Cernadas. Cernadas, just currently holding up my computer. It is as follows. First, we have to analyze the signature, semantics, and syntax of every logic. If the logics are not defined semantically or syntactically in the same way, then we must redefine, or rather, create equivalent definitions of those semantics and syntax in some homogeneous setting. Say, for example, if one logic is defined, semantically defined in possible word semantics, and the other is by evaluations, then we must redefine the semantics in some algebra or some higher order, some more expressive logic, so that we can define in this more expressive logics all the rules of both logics and then join them up in a single homogeneous system. Then we must compute the unions of the signatures, the semantical and the syntactical rules. These unions are what make up the components of these new logics. By union here, I simply mean the set theoretical union of these objects. So this part is quite simple. And if it is necessary, we need to add new rules and axioms that relate the connectives in the shared language. Because an interesting property of these methods is that by definition they don't give us explicit relations. So for example, if I have, say, modality and consistency in my logics, in this case the logics I'm working with, by combining the logics, combining the modal and persistent logics, I will not get any axiom that relates this guy with this guy. There will simply be two connectives in the language of all axioms for this guy. I'll have all axioms for this guy. But if I want an axiom that relates these two guys, say, for example, if P is consistent, then it is necessary. Say, if I want this, I need to add this in my axiomatization and add any corresponding semantic rule also to the semantics of the logic.
That's what we call bridge axiom.
Precisely. This will be called a bridge principle or a bridge axiom. Okay. So the cathodic logics. First, their definition. So the cathodic logics are the result of manually combining the basic analytic logic, which is represented by this. It's simply the modal logic K that has the implication, the conjunction, and the possibility, together with the box and the disjunction, I think, I forgot, extended with some instances of the Lemon-Scott general axiom, with the logics MBC, BC, CI, and PI. The Lemon-Scott general, the Lemon-Scott general axiom is simply the axiom that
connected diamonds and squares.
Yes, I think about a good way to explain it, but it's a bit complicated. So anyway, so these logics, the cathodic logics then have modalities, consistency operators, and both weak and strong negations defined in their languages. It's supposed to be languages, not signatures here. We got strong negations because in part-consistent logics, I believe not in BC, but in BC and CI, we can define strong negations as being from both implication and weak negation. In BC you can too? Okay, so in... Okay, that's true. Yeah, thank you. Then, semantically, these logics are defined by a two-value possible word semantics and a three-value possible translation semantics. Synthetically, they are defined by Hilbert calculus with rules from all base logics. Like I said, it's simply a set theoretical union of the rules, and some new actions that impose a duality between the box and the necessity and the possibility. Because, as I said before, in the anodic logics, they are bimodal, they don't have negation, so we can't define one in terms of the other. So, once again, what I just said before, in spite of the presence of both modality and this consistency in their languages, they don't have any axiom that explicitly relates them. They don't have any bridge principle that relates these two components. So, if it were to be needed, or if it were to be interesting to have an axiom that relates those two components, it would need to be added specifically for whichever situation you're using those logics with. So how do we get this with algebraic fibering? So recreating these logics by the means of algebraic fibering is not particularly easy, though it's certainly not as complicated as doing so manually. So the signatures and axiom systems of the cathodic logics are simply the set theoretical union of the components of the signatures and the axiom systems of the anodic and LFI, partially consistent logics. Though the rules are slightly different from the original definitions because the method follows because of peculiarities of the method. But it's not nothing really big, the difference. So the semantics, however, are quite a bit different. So due to the fact that neither logic is true functional and both logics are defined in very different semantical ways, we have to express their semantics in some more expressive metalogic or some more expressive formal system. So in this case, a logic known as CEQ, which is a conditional equational logic, is utilized to represent those rules. In this logic, all formulas are basically equations between terms, conditional equations. So there might be an equation which implies another equation. And these equations contain symbols from both the object logics, so the anodic logic, MBC, BC, CI, etc., and the meta logic, being CEQ itself. So, as an example, this is the evaluation rule for the conjunction. So, this component here in red is a conjunction from the base language. This could be from MBC, could be from the anodic logic, whichever you choose. This V is our evaluation function. This is what evaluates a formula. This funny symbol here is the conjunction in CUQ. And then this is applied to the evaluation of both base formulas. What this is telling me is that to evaluate a conjunction in, say, the MBC, it is equivalent to evaluate in CUQ the conjunction of the interpretation of both the formulas in the both the conjuncts. So the evaluation rules of both base logics are represented in the meta logic CUQ, and the union of those rules is computed to then obtain the evaluation rules of the final cathodic logics. Because these rules like this are done for each logic, so I have to define these rules for the anodic logics, then I have to define those rules for whichever other LFI or consistent logic I'm using. Then I have to compute the set theoretical union of both of these, and then I can get the evaluation rules for the cathodic logics. This process guarantees that soundness and completeness both will be preserved under some reasonable conditions. If I recall correctly, it's that both logics have implication, conjunction, and disjunction. So some conclusions. Okay. The results indicate that the goals set out for this work are achievable, and that it will not only be possible to recover the logics originally proposed, but also that new ones will be able to be defined by means of the method of algebraic fibering. So in spite of the fact that the logics being recovered or that being redefined have a different semantical structure than the original logics, so the logics being obtained by the algebraic fibering will have some slightly different semantical structure, and I think not syntactical, but semantical, and it will require some minimal efforts to transform these new definitions back into the original definition. So it was originally defined in Juliana's papers with a three-value possible word semantics, I think it was, and the possible translation semantics. And so it will take a bit of effort to go from CEQ valuation rules back into that, but it is easily achievable. So nevertheless, should our goals set out for this work be achievable, we believe these logics will be applicable outside of just being funny, being interesting logics. These are my references. Thank you very much.
Thank you, Miguel. Very interesting. Anyone has questions?
I understand well you are proposing to encode in certain manner or break configure the sense the logics that Miguel has in the
Yes.
model technology as opposed to firing by using a technique of firing non-functional logic.
Yes, because neither are true function.
Okay.
Because the
Using
practice-
that semantic platform representation of evaluations.
Yes, because the practice negation is not true function and neither is modalities.
Then you want to reintroduce that logic as a particular case of firing and not.
Precisely.
Nice. That's perfect.
Very nice, yeah. This is a good project on applying techniques, so we are doing that book here behind your computer. So the book is supporting this weekend. That's a good project because these techniques are so very difficult. And this particular program was proposed by Professor Cristina Cervantes. Because she is an authority in this kind of firing, this algebraic firing, also introduced by the Portuguese colleagues there, which sort of abstracted this original Lógica firing, much bigger, much wider. That's a fantastic tool for combining logics, and I think your work is going in the right direction.
Questions? I have one. It's not exactly a question, but it's something that I was curious. You talked that you have to go to a semantics that is different from the mix of both, right? It's CQ.
CQ, yes.
Yeah. My point is just that perhaps you may not want to discard CQ as a semantic possibility so quickly, because you were telling in the end, well, we can return to the original semantics, but I think having a new semantics can bring new lights into what is this combination between prior consistency and modality.
Yes, no, it was merely not entirely to disregard the CQ semantics, but it's not, it was not to, sorry, I'm getting confused. My goal in saying that was not to say that we can disregard the semantics, but we can have both this semantics and the original semantics she had in her papers. We can have both of these definitions for the logics. And we can mix and match or use those whenever, use whichever is most applicable to whichever problem we're currently tackling. It was more in that direction that I was talking about.
Questions? Anyone else? We still have time.
We have some time, yes.
Okay, so thank you, Miguel. Okay, so now I have Guilherme's presentation. Guilherme is a PhD here from UCLA. He's done his PhD in supervision of Marcelo Bonilha on structures, on deterministic semantics, and now he's a postdoctoral researcher at Israel, right?
At Bar-Ilan University,
Yeah.
yes.
And he will be talking about theory combination and overview. Then,
Yeah. Well, this is a bit too broad. I'm going to actually talk about polite theory combination. This is our group symbol. It means this talk is about theory combination, essentially. So, let's talk briefly about SMT. So, SMT is a broad area of research in theoretical computer science, but also with several applications in applied computer science. So you have a problem, and you translate this problem into a theory, which you then transform into a solver for this theory. So this is some aspect of the problem. Say if you have a factory and you have to keep within some security threshold for something. I don't know a lot about the applications per se. So what you need is a theory that deals with real numbers. But the actual problem that you want to test, that your machine is working correctly, then you translate into a formula that you feed to the solver, which will answer unsatisfiable or satisfiable, ideally. So I work on this specific step here. So I take a theory and I try to find a solver. And I do that by doing theory combination. I mentioned here a few restrictions. We are dealing with first order logic, usually many sorted, but for the current presentation we can assume just one sort. And the signatures are countable because applications usually require that. And we are only working with quantifier-free formulas for now, at least in this presentation. And well, why do we do theory combination? Because it's not obvious. That's why some people work on that. To give one example, if were it obvious, there would be no need for people working with theory combination. But a classical example is, well, Pressburger arithmetic is decidable, and so is Scullin arithmetic, but when you combine the two, you get piano, which is not. So combining theories is not trivial, and I'm going to talk a little bit about this today. So this is actually about a paper we just got accepted that solves a 20 years old open problem. We are very happy about it. So the first method to do theory combination was Nelson and Open. Then came shininess, which took a long time. Yes, you can notice that. The same year, however, another method came up, politeness, which says, this is very pictorial. If a theory is polite and decidable, and the other theory is decidable, then combining the two, and I mean combination like the model shared by the two theories, then the combination is decidable. This is the main result we are going to talk about today, which is false. There was a mistake in the proof, but that was corrected 5 years later, which changed politeness to strong politeness. This is correct. This we didn't know whether it was correct until now. I'm going to give the counterexample.
here is another method that it's somewhat well known, and these are the most important methods. And Nelson Open, shininess, gentleness, and strong politeness. So, why care about politeness if we know that strong politeness works and we were not sure whether politeness worked? Simple. To quote Ian Stewart, because politeness is simpler and we really want it to work. So people tried everything to make politeness work, and they couldn't make work because, as I'm going to show, it doesn't work. So, when I started my postdoc, just tell a little story. My PI, Yuni Zohar, he gave me 4 problems to work with. Well, first of all, we want to prove that all polite theories are strongly polite. This will imply that politeness is enough for theory combination because of these results here. Then we prove that politeness implies decidability. So polite theory combination becomes a simple thing. If one theory is polite and the other is decidable, then we get a decidable theory. This is a bit unrelated to the project I'm talking about right now. So we had these 4 problems, and just to give a very basic idea, politeness is a nightmarish property to have for a theory. It's very difficult to define, to work with. The basic idea is a theory is smooth when it has all bigger models, meaning if a quantifier-free formula has a model, then it has models of all larger cardinalities. This is a step in defining politeness. An arrangement is just a formula encoding an equivalence relation. Here you can see that X is one equivalence class, Y and Z are another equivalence class, and this is codified by this formula. So, finite witness ability is another property that says that you have a computable function from quantifier-free formulas into themselves, such that the formula and the existential closure of the witness are equivalent according to the theory. Okay? And second, if the formula is actually satisfiable, then there is a model where every element corresponds to a variable in the witness. And this is very strong. And the idea, although the definition is so difficult, the idea is simple. Is that we are trying to get the smallest possible model. So, if you only have as many elements as you have variables, that's quite small. That's quite small. Strong finite witness ability is almost the same property. It's just that you have to consider any arrangement. If the witness plus an arrangement is satisfiable, then there is a model that satisfies this formula, where every element corresponds to a variable in this bigger formula. This sounds simple, but it's not. Well, politeness is just finite witness ability, this thing plus smoothness, and strong politeness is strong finite witness ability plus smoothness, just to mention. Look, consider the theory where models have at least size 4. This is a witness because I can shrink the model to have only the variables here, And if I shrink too much, say phi is the tautology x equals x, I don't have enough variables to get a model of t, then I just consider these extra variables. These are fresh variables, by the way. But this is not a strong weakness, because I can take the arrangement that ruins everything by making the new variables all the same. I can fix that with this strong weakness, which requires that the elements are different. The proof that this is a strong weakness is not trivial. Although it sounds very simple, it is usually very boring to prove something is a strong weakness. How long do I have?
About 15 minutes.
Oh, okay. I still have a lot. So, an unfortunate theory. I call it unfortunate. You will see why. Because it ruins something. So, take your favorite non-computable function that returns 0 and 1s. Say if a Turing machine halts or not. This is my favorite non-computable function that returns 0 and 1s. What I do is I take the complement of each element and add just right after it. So 1, 0, 0, 1, 1, 0, 1, 0, and so on and so on. This is a very nice non-computable function. What I do with this non-computable function, I won't give the axiomatization of the theory, because I don't think it will help in understanding what the theory does. So let me say, so the function that I ended up with starts with 1, 0, 0, 1. So I here give a brief explanation, but I don't think it's that helpful. Because I start with 1, let me start the models of the theory with a loop. This is a model of the theory. Now, because the second element in the sequence is 0, this means that I have to add an element to the model to get another model, but the function can't be a loop in this element. So I only have one option. There is only one model of this theory with 2 elements, is this one. Now, because the next element is 0, it means I have to add another element to our models, where the function here cannot be. Think of this as just a graph. I mean, I need to add another element to this graph where the arrow is not a loop. So now I have a few more options. Well, actually, only 3 of them are non-isomorphic. These 2 are basically the same. But all of these are models of our theory. And now, I didn't have the space here, but because the next element on our sequence is 1, then what happens is that I need to add another loop, which gives us these models with 4 elements, which are definitely not all isomorphic. So, this is a theory. This is a first-order theory with only one function, one unary function. So we get these nice graphs. And what I say about this theory? What I say about this theory is the following. It is smooth to see that. Let's take a model here. Say this one. And notice I can increase this model while keeping all old relationships between elements. Thinking model theory, keeping the types of these elements. So the theory is smooth. The proof is actually rather involved, but you have to trust me because I didn't write out the proof here. The theory is is finitely witnessable. I'm not going to try to convince you of that because it's not, I don't think it's within the scope of what I wanted to say here. But the idea that I think the people that defined politeness and strong politeness missed is that in a way, strong finite witnessability is saying I'm able to predict the structure of all finite models. Okay, I said before that I'm trying to predict the smallest model. But in first order logic, you can always consider one variable different from all other ones. So what I'm doing is that I'm predicting the behavior of all finite models. Finite witnessability is weaker. In what sense? It's enough to predict the behavior of models at intervals. And that's amazing. That's an amazing thing. So, because I define the sequence in this way, I don't know how the odd models of the theory are going to behave. But I know the models with even cardinality must have the same number of loops as the number of non-loops. To check this, so here we have an element that doesn't lead to a loop, and we have one element with a loop. Here, I can predict without knowing the non-computable function that I started with, but here, I know that I must have two loops and two elements that are not in loops. So the behavior of this theory is predictable at intervals. In this case, the simplest interval, even numbers. So this theory is finitely witnessable, but is not strongly finitely witnessable, and that's amazing. Because the first problem that I wanted to prove in my postdoc, I proved the opposite. I found a counterexample, which is great. I mean, we were very happy when this first came up. It said that politeness is actually weaker than strong politeness, but it's nice that now we know. But this doesn't imply that politeness is not enough for theory combination. Maybe this is still true. And this was an open problem for the last 20 years, until we noticed something in this theory. An unfortunate combination. You can see where I'm going with this. So, let me define a very simple theory. It has infinitely many predicates. And when one of these predicates is true, then the theory has precisely as many elements as the index of your predicate. So if P3 is true, then the model has exactly 3 elements. If P17 is true, the model has 17 elements, and so on. This theory is decidable. It's easy to see why. You just need to look at conjunctions of literals. Easy stuff. And you notice that these PNs are just a convenient way to codify the cardinalities of a model. So if you have PN, you know how many elements you have without having to resort to quantifiers. And then we have a recipe for disaster. So the theory I told you about with the graphs and so on is polite, and it's decidable. To prove that it's decidable is a bit trickier, but the idea is that for any function, you can find a big enough model of this theory that has a submodel that satisfies your quantifier free form involving functions. Not important right now. This theory I just told you about with all the predicates is decidable. So if polite theory combination were possible, then the combination of the two would be decidable, but is not. Why? To see that is like, suppose a model, suppose a model has n elements, m are in loops, and then you consider this formula. I want to go to a model with cardinality n plus 1, and I want m plus 1 elements set in a loop. But if I know how to decide the satisfiability of these formulas, then I can predict the behavior of this theory, which I can't because I constructed it using a non-computable function. And that's our paper. That's the entire paper that got accepted to Kate, because, okay, there is more stuff in the paper, but the basic idea is just this, is this one slide. Because it was an open problem for the last 20 years and people kept trying to save politeness and no one could because you can't. So the second point that Yoni gave me to work on my postdoc was solved again in the negative. We gave a counterexample again. Great, we are good on, with that. So, 5 minutes, okay, I'm really in the end right now. So, future work. This last point, we also found a counterexample. Great, it's not related to this one. We are submitting it this week. And this last point that he also asked me to work with is also done, but not by us, sadly. Someone else found the maximum decidable fragment of the set theory in CVC5, which contains cardinality, which is a very nice paper, but we didn't write it. So now let me just go back to our short little story of theory combination. So we have 1, 2, this one doesn't work, 3, 4 methods for theory combination. And well, once we found a counterexample, we thought to ourselves, well, let's classify which ones are the counterexamples and which ones work. And this led to some amazing new results I talked about other day here at CLE. That we started coming up, thanks to the ideas involved in this question, we started coming up with new combination methods, and people took 46 years, that's it, until today, to come up with 4 combination methods, and in 2 months, we have 12 new combination methods or something like that. Because we found the right question to ask about. Let's classify polite theories. And that's something I'm going to talk later, some other day when the paper is actually written down. So, thanks for having me. I just wanted to say, I know there are a lot of people that are not here from Brazil. The people from Brazil know that I'm a bird watcher. This Saturday is the global day for bird watching. So it's a nice way to go, it's a nice day to go bird watching here in Brazil. And the following weekend, if you happen to be in Brazil by then, is the National Conference on Ornithology in São Paulo, which is also very nice, even if you don't want to listen about the reproductive behavior of the common pigeon or something like that. It's still an amazing event. This is from here. This is from Campinas. So yeah, thanks very much for the patience.
Okay, thank you, Guilherme. We have time for some questions. Walter.
So, yeah, thank you, very nice. So besides destroying theories, what you intend to do in your
Yes, yes. We are very good at destroying things, but from the ashes, as I mentioned, we came up with something amazing. You know, by trying to classify the polite theories where you can combine them and where you cannot combine them, we started finding new combination methods. And actually, as I mentioned before, we kind of have an algorithm to generate new combination methods.
They should be decided, all of them.
Yes. And come on, 46 years, people came up with 4, and that's something I didn't mention, is that shininess and strong politeness are actually the same. They are just disguised. So there are actually only 3. 46 years, 3 methods, and in 2 months we have like 10 or 12, I lost count, of new combination methods. So something is coming from this destruction of theory combination, something positive. So I don't think our work is just depressing news for the theory combination people.
Destroying and creating.
It's destroying and creating, yes. By the way, let me just say something. I actually had a talk involving probabilities to give here at RatioLog, but I mixed up the submissions and I submitted that talk to EBL and this more interesting talk to RatioLog. So the people on RatioLog got the most interesting results we have so far, and the people at EBL will have to do with some probabilities. Yeah.
Very good. Okay.
Yeah.
Anyone else? Please, so thank you, Guilherme.
Thank you.
Sério?
Okay, so for this last presentation, we have Felipe Abrão here, which is supervised by Italo Ottaviano, postdoctoral researcher, and he will be talking about zero knowledge, one-way communication, problem beyond theories, structures, and probability.
Yeah, good to pick up from the Walter line that comes from the field that destroying other people's theories is what we do.
That's good.
Yeah, and it turns out that pursuing this kind of living already showed to happen. To allow us to achieve the maximum or the best we can do. Unfortunately, the best we can do is not always achievable. In fact, it's achievable, but not always computable or determined or predictable. But that's the price you get for avoiding paradoxes. So we all know that. So I picked one of the researchers I was doing last year. I was abroad, with this thing, the ones we are writing these 2 papers, which are follow-ups from one of the previous one anyway. So I try to present the problem. The problem is very simple and very basic. Possibly you find impossible to solve, which is what I'm trying to convince you it's impossible. We do a long shot in the dark and I beat the target. It's kind of magic, but it's kind of expected of this field. So, sorry, I forgot to start. I have 20 minutes? Yes, in 5. Let's start with this problem. We have an unknown agent, and he's trying to convey some message, convey some content, convey some mathematical object. We'll talk more about that later. So, and the issue is, how can I decode, how can I interpret correctly what he's trying to convey to us, given that we don't have any prior knowledge about the agent. So this problem has 2 aspects. One we're going to talk on the next slide. One is that this channel is just one way, and the other, of course, is the one I'm already explaining this slide, which is the zero knowledge property. So so clearly, if anyone knows has some idea of this kind of problem, is related to techno signatures. Techno signatures is identifying, detecting, or classifying, and then hopefully interpreting correctly traces left by another intelligent agent that you don't know what. For example, we're going to talk about this. Let's skip the surprise for the next one. So important thing to highlight this problem is bidirectional or invertible. That is, we have zero. The sender also has zero knowledge about us. We have zero knowledge about them. And he has to encode somehow in a manner that we can decode. So, and we have to decode given that we don't know how the other agent encode, right? So let's keep this in mind. To clarify what we are ignorant about. We are ignorant about a lot of things. That's why this problem seems impossible. One thing is the encoding-decoding scheme. For example, how you have an encodable object, like an array, and you have, for example, a multidimensional array, and you have to project it in the unidimensional string, for example, to pass through a signal wave function and transmit it to a signal or electromagnetic wave, for example. Then we can be a little more dramatic and can be ignorant about the computational model that he used, for example, through machine or one machine. Anyway, any kind of model, abstract or physical, about the programming language and about the computational appliance that is made available to this other agent. Okay, so we can be a little more dramatic, and it comes to the heart of this event, I believe. That's why I picked this research, is that we can be ignorant about the probability measure that the other agent picked or chose to be the best one or the optimal one. And we can be a little more even dramatic and can be ignorant about the mathematical statistical framework for which he's based inferences on the functions that he can build their probability measures. And then it continues. You can be even ignorant about the formal theory for which this other agent is formalizing the mathematical statements, theorems, and verifications, and proofs, so on, using all of this other apparatus up in this hierarchy. And finally, we can be even more dramatic and be ignorant about the mathematical structures that this other agent didn't fundament the mathematics, whatever structure or family of structures or logic. We're going to talk more about this later. He deems fundamental. So this is classically a chain for them. What holds for the bottom holds for the higher levels in this kind of illustrative hierarchy. All right. So I talked before about one-end channels. Just to exemplify, to explain it better, one way is just you have a communication, and you can only send communication. So the receiver agent cannot send back communication to help decode what he received in the first place. So it's basically a simple property. But this is not an imperative property. For example, we're going to talk in the last slide about zero knowledge proof. This kind of property doesn't forbid you to achieve results. The zero knowledge communication property is the more interesting one, of course. That is what we have been explaining earlier, that receiver agent has no knowledge about the emitter agent. So this is what I think this is okay to understand, I believe. So just to exemplify the classical communication theory given by Shannon, and use it nowadays everywhere. This is a little bit expanded on the this colored text is my adding to the original diagram draw by channel. So we have the channel, the communication channel here, and the expressor is an agent, and then he applies an encoding according to their methods and theory. The channel is subject to some stochastics, like the form of noise, for example, and the receiver agent applies the decoder based on their methods and theories, and interpret the message sent by the signal. So this is already one way where might be noticed it. So, but apparently it's one way, but in fact, both the receiver and the sender has to a priori agree about a decoding-encoding method. So the theorems of classical information theory works if the receiver and the sender happen to have the same encoding-decoding speed. That's not what we are trying to tackle. We don't have this assumption in mind. And we are not going to discuss how much it depart from the classical information, but in the papers there is more discussion about it. So yes, I believe some of you might be wondering what we are talking about. Yes, we are talking about agents. So agents as assisted by us, right? But you have to remember that the problem is symmetrical, where it's in fact bidirectional and invertible. So we are also talking about how so I'm kidding, but I'm kidding. These two papers, they are not published yet, submitted but under revision. Make a little bit of a buzz in the field. So people from SETI wrote this known peer-reviewed media coverage, and some researchers find this interesting. So if you find this interesting somehow, I can send you the links. I don't know how they are using to decode in SETI in other departments, but we don't know. I guess actually just the PI, my supervisor in last year, probably is more in contact with them, but I have no idea how they are using what we did. But okay, so this problem, I guess, is interesting, is difficult, it's mind-blowing, but what you have, in fact, what I did the theoretical part in the work, right? I proved the theorems. So what I'm really looking for, and in my project here with Italy and Clay, is that this problem is equivalent. Sorry, if not equivalent, it's not the same of studying what is the foundation of mathematics. And of course, the problem is bidirectional or invertible. So it's also about how mathematics or our mathematical constructs think about the mathematics we do. So let's start the theoretical method. This is our information theory. How many of you know about information theory? Okay. Right. So this is my one-stop shop slide. Sorry. To try to explain our information theory in the more compressed way. The pun is not intended because our information theory is about compression. So the more interesting fact, two of the main results are that finite objects are biased towards simplicity, and infinite objects, mathematical objects, are biased toward true randomness. True randomness, to differentiate from statistical randomness, we can come back to this problem later. But yes, the problem what is randomness in mathematics was solved by this field, and avoid the other paradox that the statistical methods are always prone to. So the most important part is the bottom, the top, which is also interesting. That is, every infinite object that is random is basically dominates everything. Although we have mathematics, it's interesting, but we are not talking to this problem for now. Here, some of them may notice that this is the algorithm complexity, and now I'm on purpose reframing it in terms of formal theory, which is equivalent definition. And this one is more important for us now, which is the maximal semi-measure. We have measure theory, and this one is proven to be the best one can do for every kind of measure you can formalize, so that it tops every other measure you can devise. And this is called the maximal maximal or universal maximal or optimal semi-measure. So it has to specify, is a measure that also satisfies any measure, the properties that any measure needs to satisfy, like the sigma, utility, and so on. And what happened is that this measure, on top of dominating every other measure you can devise, is equivalent to this is called the universal coding theorem. So this theorem shows that this measure is basically equivalent to the algorithm complexity. Here it's taking the logarithm, so it's the log of the measure, and any similarity to the entropy is not a coincidence. So here we have the algorithm complexity, this one here, and this one here you can call universal probability or universal a priori probability. It's just the sum of all possible theories that can construct your object x. So it happens that this kind of particular probability distribution, which is called universal distribution, given by this measure, dominates everyone, other one you can devise. And this is the reason this kind of theorem is deemed to be the one to tackle universal inference problems. They want to truncate, for example, Bayesian regression. This can be interpreted as the posterior of all posteriors, or the prior for which you can never be wrong about, or the prior for which every posterior is going to converge. Anyway, just to give a statistical interpretation. The likelihood, the universal distribution, to compute the universal distribution is the likelihood, the best you can achieve to take inference. Anyway. Okay. Right. So we have this framework is well established to make approximation methods. It's an active field to devise new approximation methods to this universal distribution, and you can always keep improving the errors for any inference you devise. You apply it this kind of this theorem on top of it and improve the errors. There are many works on this. The most famous one is a paper, I guess it's the miraculous distribution, something like that, of people claiming that it solves the Arkham rays, but we are not going to discuss about this. We're going to discuss about the problem of information content in structures. So the infinite case, I said I'm not going to talk about it, but these people working on the infinite structures. Here are graphs, here are structures in general, that Morpheus does not preserve a root information, or does not preserve your formal theory. Your formal theory is never enough. Sorry, the isomorphisms are never enough to characterize what formal theories can characterize about structures. This one uses Radograph. Radograph you may be familiar with. It's just an example of random graph that, for example, can be used to prove Scolin's theorem and alternate proof to Scolin's paradox. This one is infinite structures in general. But the finite case also started being developed recently. We worked to prove that distortion, this kind of distortions, brought about by isomorphism also happen to work and finite structures, which is interesting because for automorphisms, random structures are robust automorphisms, but they are not isomorphisms. Finite structures, and then these two works are developed here in Clay before my research internship abroad. But this one is going to be presented in Recipia. It's about incompleteness, stronger forms of incompleteness derived from this kind of distortions from morphisms in general. And this is the part that poses a challenge to applying the algorithmic coding method, how they call it, to find the optimal models for any kind of phenomenon we have, which people do. But now we are dealing about arbitrary structures. It poses a problem. We'll talk more about that in the paper if you want to discuss it more. All right. So now is the fun part, which is kind of also simple. How we tackle this problem of decoding the unknown, or decoding the message sent by an unknown source. We're going to show the theorem, but the idea is simple. You first start compressing the sender, compress them sufficiently the object, also the multidimensional space, the structure with the signature, so on. is also compressed with respect to the object. And then the receiver agent start applying perturbation transformation on the sequence as much as possible, and we build the landscape of complexities that we achieve from these perturbations. And we get that for sufficient large objects, we pick the message with the sharpest and deepest downward spark. We're going to show you the picture. And we happen to estimate the best answer. All right? Any similarities here? You may be wondering from people from statistics and from classical information to Fisher information, and maximum likelihood that is not also coincidence. All right, so a message is nothing more than an object embedded in a multidimensional space, and as I said, it can also be generalized, so in this downstream hierarchy. For example, you have an encodable message, you can have a three-dimensional object, and then generalize to any dimensional object. In the discrete space, maybe you have a continuous space. Okay, you just need to work with an encodable continuous space, for example, using Fourier's expansion, series decomposition, and then generalize a little bit more. You can just need to work with an encodable structure defined by encodable signature. Hopefully, I think we else explained what is a signature before. And then, for example, you can also generalize to a model. This object embedded in a multidimensional space can also be a model and defined by its own signature, truth assignment tables, logic, axioms, and so on. So basically, he may try to transmit his own mathematical knowledge to the receiver. Right? Okay. A perturbation, perturbation, nothing more than a program, arbitrary Turing machine, if you want, that transforms the object and the multidimensional space. So it's not only transforming the multidimensional space. This is the part that distortions came to happen. May try to happen, so we managed to avoid it. And the probability distribution measures are arbitrary, like we wanted. So pick the one we want, and we achieve the desired result. So this is a theorem. I don't expect to explain everything here, but here just conditions just mean that the multidimensional space needs to be sufficiently compressible. And this one is not necessary, but just to complete this, we put a upper bound on it. Actually, the more perturbations you take into account, the better the result. But anyway, and this one also says that the object needs to be sufficiently compressible. And then for any other possible candidate, is going to obey this interesting limit here. That is, starting for a completely unbiased distribution. Here, that's the problem that Bayesian and frequentist likelihood and Bayesian parameter estimator are conflated, because we are dealing with universal distributions, and any theory is basically subsumed into it. So this is expected to happen. So, but the bottom line is that starting from completely unbiased or unknown assumptions about the perturbations, you happen to have to achieve that using the universal distribution strongly dominates any other method you chose to be the optimum one. So just to explain what you do your best, pick the formal theory, pick the statistical framework, demonstrate that this statistical framework is very good or good enough for what you want, and using algorithm probability eventually is going to be better to estimate the optimal solution than the previous chosen optimal method that you took in the previous slide. All right. So This is just the image I talked earlier. This is empirical results in the paper. For example, this one is the irreversible message. Do you know the irreversible message is the one from 1979? I don't know. That they sent recklessly to the space, trying to locate us in the universe, I guess. And they are based on the fact that we find prime numbers to be interesting, but this is completely outdated. What we did here is perturb the signal randomly, and the deepest and sharpest downward spike in the complexity happened to. This is one of the results. We have one, but this is one more graphical, more interesting. Happened to be the right model. So we also benchmarked with other kind of complexity estimators, and it happened to work. Right, so finally is the last slide. We're not going to enter in this problem, but if you find it interesting, you would like to discuss more about it, please reach out. This problem is related to zero knowledge proofs, not only because of the nomenclature. Zero knowledge proof is interesting because it's one of the examples Friedrichson mentioned that we rely on testimonies that we don't know, cannot verify. Actually, this one we don't have to rely even on authorities. Just we don't know the true content, but we can verify that the other agent is true about the proof, even though we don't know what the other agent is proving. So this is interesting. Of course, we have a mathematical is related to channel coding, information theory. It's kind of a mathematical telephone game. I don't know. It's whisper down the lane. I don't know. There's many names, but it's a mathematical version of how to solve universally solve the telephone game mathematically. Statistics already mentioned that is related to feature information and complex Bayesian parameters estimation, and of course complex systems, which is the one I'm more interested in right now to use to explain why nature, why biology presents emergent complexity. And it happens to have some interesting connection that the shape of the objects we have in nature, of the systems, happen to be useful to decode the complexity of the very system we are interested in measuring the complexity. That's all.
Thank you very much, Felipe. Now we are open to questions. Walter?
Felipe, when you mentioned incompleteness, you're thinking about something like enchanting constant or this kind of incompressibility. I mean, how we get some kind of any kind of
This is one example of an uncomputable function. This one, and this one, and this one. They are
uncomputable, but not really completeness. In the sense of incompressible.
They are. This one is a quantity that is incompressible, but to calculate the number given by this function, I mean the value given by k plus x is the input, is also uncomputable. This one is the chasing randomness, right?
This one is chasing.
You have an infinite object. You can also have finite objects that are incompressible. But the changing so-called halting probability, omega number, or changing constants is an infinite, it's a real number.
Okay, anyone else?
It's more of a theoretical question. So from what I gathered from the slide you said, the method is like if you try and add complexity and try to see, actually adding noise and seeing which is at least complex. It's basically like, trying other methods if you're hoping you find something that works, no matter don't really know nothing at all about how the data is provided and sent to you. I guess that is really the only option, right? To just guess and hopefully you get a good guess based on that.
Or yes, I think it has to do with it, but the main engine behind this theory is that when you consider a large enough amount of perturbations or noise, like you said, transformations, then the complexities of the results you get from these perturbations are sufficiently large than the complexity of the object you and the space you are sending or you are encoding. And then, even though you cannot calculate, you can only approximate the value. This is called semi-computability. You can approximate the value, and you never know how close you are to the optimal value. Being able to make a sufficiently large number of perturbations allows you to use a computable method and tell apart or estimate the divergence from the complexity using the landscape. It's like to tell the right one, even though you can't calculate. This is interesting. So even though you can't calculate the exact complexity of this message, right? So the object embedded in the right dimension, you can estimate which is the right one, even though you never know the complexity of this right one. Okay, makes sense. Thank you.
Hey, I want your help to better understand one of the theorems you showed us, which is that finiteness is biased towards simplicity. And you said it's a theorem. I feel out of my depth because I have no idea where that came from. I'm familiar with something called Solomonov induction.
Which is this one?
Yeah, but I never saw it as a theorem. I always saw it as an arbitrary prior where you privilege shorter algorithms just because. But you said it's a theorem.
Yes.
Can you contextualize to me why it's a theorem?
Yeah. So Solomonov, Chetty, and Komogor were working in the same related problems, but from different backgrounds, different motivations, and they can actually live in together in Komogor, not exactly Komogor, but anyway, to this theorem, which is, and then later, in the 90s, they built a method for Solomonov induction based on this theorem that proves that you can always find, there is an optimal way to find the optimal solution for any computable set of phenomena. But it is semi-computable to find the actual optimal model. So this is what this theorem says.
I don't know if I get it fully. Like, I get the idea that there's a shortest program that encodes the data you have. And I get the idea of true randomness being incompressibility. So I have these two building blocks in my mind.
Right? Which is the main one.
Yeah, but there's something I don't get. Like, it's a theorem. What does it say? You say that it's an optimal program relative to what objective?
Right, so you find that you pick your optimal inference method that you like.
Okay.
And then this theorem says that using algorithm complexity or using Solomonov probability, we're gonna eventually dominate or improve your solution, or your optimal method is gonna be suboptimal in respect to the optimal maximum semi-measurable algorithm complexity, which means that compressibility in terms of universal compressibility by universal machines in the asymptotic limit dominates every possible optimal inference method you can devise, which is kind of intuitive if you think about it, because we're considering every possible theory we have made devise here.
Well, that's fascinating, and I will read more about it and think more about it and probably email you. So thank you.
Okay, thank you.
Okay, we are out of time, so thanks for listening. Let's begin the last block of the day. Now, I present Mikhail Bombassaro from the Federal University of Rio Grande do Sul, and he's working on his master's degree, and his work will be from temporal propositions to tense logics. Mikhail?
So thanks. First of all, I want to thank the organizing committee and universities involved in the event, professors who welcomed me very well. And today I will talk about tense logics. That is my research, and in my method, I thought that I can read some paragraphs of a paper that I'm reading and comment some aspects of my work. And well, today I will present the temporalist and eternalist distinction as two paradigms in the history of logic. And well, I aim to show how tense logics presuppose temporalism. Because of this, I also must introduce the presentist conceptions underlying the introduction of tense operators. And finally, reasons will be shown to accept temporalism in logic. Well, so let's do it. The first and seminal assumption that I aim to present in this talk is what I understand as being two paradigms on the stability of truth values. That is, fundamentally two paradigms in logic. By paradigm, I mean roughly what Kuhn meant in his work, or what remained of this notion following the reception of the structure of scientific revolutions. And I said roughly because, of course, the main subject of the notion of paradigm are the empirical sciences. And a paradigm in abstract science, like mathematics or logic, would be of a different nature. I will not dwell on this difference on this talk, but I think it can be easily intuited. Perhaps we can talk about this later. Well, the notion that the proposition can be true at one time and false at another was well accepted since Aristotle's works until the rise of contemporary logic. In the end of 19th century, Frege brought up the thesis, which is central in the corpus Fregeanum, that there are no temporal propositions. Every apparently temporal proposition carries between itself as a constituent the time of its utterance. In this sense, represented is eaten by F and Socrates by A, a proposition like Socrates is eaten is no longer analyzed as Fa is true at a time t. Instead, the contemporary view analyzes it as Fat, which t as an argument of the function, which eternalizes the proposition, formally understood as genuinely temporal. The first notion is called temporalism, and the second notion is called eternalism. These two notions are the two paradigms concerning the stability of truth values that I mentioned. The first holds that the truth value of a proposition may not be stable. The second holds that the truth value of a proposition is unchangeable, eternal, always stable. Consequently, temporalists assume that are genuinely temporal propositions, that is, such that can be true at one time and false at another time. While eternalists assume that are no temporal proposition and that this temporality is an appearance of natural language that in rigorous logical language must be avoided with notational clarity. Okay, the possibility of a paradigm in the field of an abstract science then must be understood as the presupposition of my assumption today. The most important pillar of my thesis is that there are these two paradigms in logic. Temporalism and eternalism, they are byproducts of even larger paradigms, without a doubt the most relevant ones in the history of logic, traditional Aristotelian logic and modern logic. My point, however, in the end will be to defend that the paradigm that is a byproduct of traditional logic's paradigm should have been largely maintained in the development of the contemporary logic. As we can see in Kuhn, for example, he says in the structure, when in the development of a science, an individual or group first produces a synthesis able to
attract most of next generation's practitioners. The older schools gradually disappear. In part, their disappearance is caused by their members' conversion to the new paradigm. But there are always some men who cling to one or another of these older views, and they are simply read out of the profession, which thereafter ignores their work. Well, I defend that temporalists, which are few among the logicians of our times, simply read out of the profession, which thereafter ignores the work. Because they are these men who cling to another view, to another paradigm. This is why tense logics such as those formulated by Arthur Prior are unacceptable by many contemporary logicians. Committed to an old paradigm about the stability of truth values of propositions, Prior bases his logics on this, as we will see, and because of this, his works formulate something like a marginal extension of classical logic, located on the peripheries of standard knowledge, and which, when recognized, is treated initially with distrust by the majority of logicians. Okay, so let's talk about tense logics and history of tense logics. Okay, in a few words, in 1941, John Nehemiah Findlay, in his paper Time, a Treatment of Some Puzzles, noted that a logical system could be constructed which attacked tense operators to temporally neutral propositions. Temporally neutral propositions is propositions uttered in present tense. Sharing this intuition, Arthur Norman Prior created tense logics as a kind of modal logic. As intuitive this association may be, Garrett Evans questioned it in a posthumously published paper, noting that is true at T does not behave like is true at W. Because of this, I think that whether tense logic is a type of modal logic is something that remains to be confirmed, but it is another topic. Preserving the postulates of classical logic, tense logic basically adds the operators of pastness, which represents the adverbial phrase "it was the case that," and futureness, F, which represents the adverbial phrase "it will be the case that" to the system, as well as the postulates required to indicate elementary laws of the system. So F and P usually are understood as the derivative of the primitive operators H, which means it will always be the case that alpha, and G, which means it will always be the case that alpha. In this form, if you have no H, not H naught, alpha, it is equivalent to the notion of of P. H means it will always has been the case that not alpha means P. And this we can formulate the future tense. And the same if we do this. So we can understand P and F as primitive operators, and we can understand as H and G as primitive operators. Prior used to use H and G in this works, but it's the same. Thus, a temporal proposition temporal proposition alpha must be understood as being expressed in the present tense, because pastness or futureness are like adverbs that can be attacked in the proposition. Let's deal with a famous example of prior changes and inventions in things. Okay. So, if alpha is I am eating my breakfast, a proposition that is false right now but was true this morning, that is a genuinely temporal proposition, instead of saying I will eat my breakfast, I could say it will be the case that I am eating my breakfast. That is F alpha. And instead of I was eating my breakfast, I could say it was the case that I am eating my breakfast. That is P alpha. And well, by the concatenation of these temporal operators, we can formulate other cases. Like, for example, if we have a phrase like he had watched the film means that in the past was past that alpha, and that is P alpha M, etc. Okay, it really seems, as Pryor said, in the same paragraph of this example, that changing the word to formulate past and future tense, modifying the verb, changing N for was, for example, is a historical accident, not a necessity of the expressive quality of the language. Some things must be noted at this point. Tense logics, as well as temporalism, do not understand all propositions as temporal. Some propositions are eternal, and this simply means that their truth value is stable. An eternal proposition is one that is either true or false in the past, in the present, and in the future. Or in tense logics notation, we can understand eternal proposition as alpha and yeah. In this sense, it is an eternal proposition in tense logics notation. Okay, so the temporalist view only assumes that are temporal propositions, not that all propositions are temporal. Also, it is notable that presentism, the thesis that presentness and reality are equivalent notions, is embedded in tense logics. I was reading today morning, and they say in a book that Professor Carnielli recommended to me, Language and Work by Richard Eckstein. And I was reading an article that begins with this maxima. First comes metaphysics, then comes logics. And I think that is very important to my work. I note here to comment with you, and so thank you for the recommendation. This is why the temporal propositions need to be expressed in the present tense in order to have its temporal modification carried out through the attachment of a temporal operator. The ideas that come with these are not so far from common sense. Well, to say that alpha was the case is to say that in a time t, alpha is present and consequently real. And now, when we say alpha was present, we are saying that there was a time that alpha was real, and now what is real is that there was a time when alpha was real, not alpha. And the analogous holds for the future tense and other tenses. Okay, with a brief introduction to the semantic functioning of tense logic, one can see how the temporalist conception is a condition for this extension of classical logic. If we assume the eternalist conception, the time of the uterus is indicated in the proposition, even if implicitly. But why? Okay, so about eternalism, I will quote a passage of Frege's Der Gedanke. Okay, so he says, but are there not thoughts which are true today but false in 6 months' time? The thought, for example, that the tree there is covered with green leaves will surely be false in 6 months' time. No, for it is not the same thought at all. The words, this tree is covered with green leaves, are not sufficient by themselves for the uterus. The time of uterus is involved as well. We thought the time indication this gives we have no complete thought. It has no thought at all. Only a sentence supplemented by a time indication and complete in every respect expresses a thought. But this, if it is true, it's not true only today or tomorrow, but timelessly. This is precisely why there are no genuinely temporal propositions according to the eternalist conception. A proposition like I am eating my breakfast, of the prior example, for them must be read as I am eating my breakfast at such and such a time. The truth value of the proposition is stable. It should be clear that if a temporal proposition is read in this way, it is eternalized and ceases to be temporal, and consequently it makes no sense whatsoever to attack temporal operators to modify the tense logics of the proposition. precisely because the time is already indicated in it. A superposition of temporal indications, if insisted upon, would evoke a kind of Kaplanian monster. You know, two index calls hitting each other in an already meaningless proposition, or kind of this. An index call, as Kaplan defines it, I think that you are acquainted with this notion, is a word whose referent is dependent on the context of use. Because of it, always take primary scope in a proposition. I, here, now are examples of index calls, and tense operators are index calls too. A Kaplanian monster, in turn, is an operator that controls the character of index calls within the scope, which violates the principle that index calls are directly referential, invalidating its role in a proposition. So, if I say, like in Kaplan's example, in some context I am not tired now, I am evocating a Kaplanian monster. This problem is that the indexical now becomes irrelevant for the evaluation of proposition, because its context of use is being undermined by the copula of in some contexts. But what defines indexicals is that it is a word whose referent is dependent on the context of use. There is a case of extension of classical logic, test logics, that can only be legitimized if the required logical and metaphysical presuppositions are accepted. Temporalism and presentism. But then, tense logics demands a node paradigm, a node view of how logic works. And this is not a subtle difference. And now I quote Peter Gitsch. It's not a subtle difference. All logical differences are big differences. How can extension of classical logic be developed, publicized and taught when the academic community is from the start against its legitimacy? Well, it is not a privilege of tense logics in the history of logics. You know, modal logic, for example, had its legitimacy doubted because of the metaphysical foundations behind the notion of necessity, and great names such as Quine, Markov, and Kripke were characters in this dispute, whose question revolved more around permissibility of a kind of essentialism than around the technical apparatus behind modal logic in the beginning. Yeah? The question there was not primarily logic, but metaphysical. These discussions in modal logical have been overcome, but tense logic has been grappling with these questions about its legitimacy in the context of contemporary mathematical logic. So, if tense logic is depending on accept temporalism, the question ends up being much more important than whether or not to accept tense logics. That is, why be a temporalist? Especially at a time when almost no one is a temporalist. As I said, mentioning Kuhn's structure, the temporalist is simply read out of the profession which thereafter ignores the work, because they are like these men who cling to an old paradigm. There must be good reasons why I advocate, like a few others, that logic should return to an outdated paradigm. So to conclude my talk, which has already fulfilled my point of showing the temporalist presupposition of tense logic, I must present some of the reasons which I think are sufficient for temporalism to prevail. Okay, first, temporalism has a greater expressive capacity than eternalism. While eternalism is more restrictive, stating that all propositions must have a stable truth value, temporalism assumes that we can have eternal proposition as well as temporal propositions. Thus, temporalism broadens the scope of logic. Also, the notion that propositions always have a stable truth value ends up being undermining logic's ability to express changes in things in events. Committed to a description of time being essentially expressible in terms of the before and after relationship, thus abandoning the reality of tense and consequently relativizing the relevance of the past, present, and future, the eternalist paradigm is a paradigm of the immutability. The world is expressed by logic as if it were a flip book, you know, with eternally unchanging images in succession. Finally, when it comes to the application of logic, talking about application of logic is important. One important remark is that Prior held a position in all his life that logic is not primarily about language, but about the real world. It's a kind of maxim of Prior's life, and he exemplifies in our quote Prior, the very simple logical truth that if John is sick, then John is sick is not a truth about the sentence John is sick, but a truth about John. Well, talking about application of logic, it is important to bear in mind that temporalism seems to be the best way to explore the concept of time in its various aspects, especially if this logic is also taken into account. With this exploratory capacity, Orston Hasley recognized that Prior did indeed develop the standard for the study of time, and with three main principles. First, the practice of interdisciplinarity. 2, reflections on formalization and always looking to the history of logic. And 3, the attention to the role of logic for the philosophy of science. Okay. So, well, I started that tense logic presupposes temporalism, and temporalism presupposes accepting that not all propositions have a stable truth value. But for this, it is necessary to accept that truth values are, by definition, possibly variable assignments, and not necessarily fixed assignments to propositions as a prerequisite for the expression of a thought, of a Gedanke, in the sense of Frege. It simply means that in one of our current logical paradigms, eternalism, the very notion of truth value, is understood in a completely different way from the pre-19th century logical tradition. I stress that in the history of logic, the notion of truth value has been defined in two distinct ways. In the older one, the truth value is defined as a variable attribution. It is, a proposition can be true at one time and false at another. In the newer one, the fruit of contemporary logic, the truth value is defined as a fixed tag, as an attribution that, once established, cannot be modified. These logics require that truth value behave not like fixed tags, but like variable tags, as I said, and this amount to be committed to temporalism and not to molded logical thesis. So, I think that in this presentation I said to you some of presuppositions behind these logics, and I talk about the history of logic too. And well, this is a paper that I'm writing. This is in construction, and I would like to hear comments and suggestions now or later. And I thank you very much for the organization again, the professors. And well, thank you very much.
Okay, thank you very much, Mikhail.
Thank
now,
you.
Anyone has questions? It's open. Bradley.
Very interesting. I'm just thinking about what Frege said. Is the idea supposed to be that when a sentence is asserted by someone in the context, it expresses a proposition where this is something in God's heaven? So it's, and that's either true or false forever, right? Because it's just this abstract. It's just expressing an abstract object, and that's an abstract problem.
Yeah.
Right? Is that the idea? And so the temporalist, what do they think is happening? Do they think different propositions are expressed, or would they not put it that way? Do they not want to talk about propositions? They just want to talk about sentences or something?
They talk about propositions, they talk about sentences, but they talk about the utterance of a proposition, the utterance of a sentence.
But they don't believe in this thing that's in a way separate from the sentence, the way Frege did. Like it's, right, I mean, once you have this idea that you do whatever work you need to do to figure out what propositions express, where it's this Platonic thing.
Yeah.
If that's what you think you're doing, well then eternalism just must be right, because
Yeah.
right. But so then the temporalists must think we're doing something else
Yes.
when we're making assertions.
Yeah. The temporalists of our times, the most important ones being Prior and Wittevich, they do not talk about the Platonic notion of proposition that Frege holds, but they criticizes it in a sense, in the sense that a kind of phenomenology. I think. And well, they differ. They make the difference about proposition sentences, and well, they accept the contemporary logics, but in the point of accept a temporal proposition or not accept temporal proposition, they differ. It's the only difference between eternalists and temporalists. That's why I said that temporalists broaden the scope of logic. You know.
Because certainly everyone can agree that sentences can be true at one time and false at another time. That's no problem. I mean, Frege would also agree with that, right?
Yeah.
But I'm just wondering, is there a temporalism, more metaphysical temporalist view, where it's not just sentences, but like propositions or something that
Yeah.
so something that's not just a sentence, or are they just committed to because what I'm having trouble is if prior wanted logic not to be about language, then it shouldn't just be sentences in context being essential values,
Yeah.
right?
Yeah.
So that's where I'm having trouble. That there's a feeling of tension between logics about the world,
Yeah.
where that's an objective thing, it's language independent,
Yeah.
and on the other hand, there are these statements whose truth values change.
Yeah.
See what I mean?
Yes, of course.
Because it feels like those are just sentences with truth values changing.
Yeah.
You know what I mean?
Yes,
Anyway.
yes. Well, I will think about it. It's a very, very good point, and I have interest about eternalist position too. I like to read about eternalists and well, the great logicians of 20th century, eternalists, Frege, Russell, etc.
And now isn't everyone also a necessitarian? I mean, doesn't Tim Williamson just think, doesn't he run the same argument for worlds? It's not that FA is true at world 1 and false at world 2. It's that FAW is just true. And so everything's necessarily true and necessarily false. I think that's his view, right? So he does the same thing Frege does for tense with worlds.
Yeah.
Okay, yeah. That feels a little weirder.
Yeah.
But anyway.
Yeah. Well, the discussion about modalities, necessity and possibility and times are a point to be worked. The one person that I read that talked about it was Garrett Evans, but in a paper that was published posthumously, that is a not finished paper, and there are some things weird in this paper, and well, it is the only work that I know that works hardly about the themes of true at W and true at T, and well, this is very, very interesting and a point to work.
Do you know this book by Creswell, The World Time Parallel?
Yeah.
I love that. I mean,
Yeah,
that's
I
all
love that
about
too.
this.
I love that too. Yeah.
It's a really
Yeah.
fascinating topic.
Yeah.
Thank you.
But thank you very much, man.
Okay, we have time for one more question.
Very quickly, do eternalists take into account that they are making the logic harder by increasing complexity?
It's a very good question. It's another question to think about it.
Yeah, they're making it much harder.
Yes.
Okay, that's fine. I mean, we are not going to change our philosophical position
Yes.
because of a technical difficulty.
Yes.
It is much harder.
Yes, of course. Yes.
I don't know, it's a point to be taken.
Of course.
Can I ask a very eager question? Yeah. What do you think temporalism is a kind of pragmatism? Depends on a distinct type of context. The time.
Yes.
Kind of pragmatism.
Yes,
Just have
that's why temporal operators is like temporal operators are indexers in the Kaplan sense.
Yes.
Yes, that's right. But I never thought about temporalism as a kind of pragmatism. But I don't think that.
No, but just now I thought that.
Yes. Well, I think that it possible can be.
The true sentence depends on the context.
Yes.
Right.
Yes. Yes.
A kind of context.
Yes.
Can I say something very briefly?
Yeah.
We don't have time to discuss this now, but it made me think that Frege's conception of objects and concepts and its relation to the true and the false, etc., it's incompatible with determinism. It's incompatible.
Frege's conception is incompatible.
Yeah. We don't have time to discuss this now, but let's discuss this later.
Because
you made me realize that.
Yeah, well, because Frege is the one who invented the notion of determinism.
Yeah, but it doesn't work inside this framework. Basically because he needs objects to exist only in the moment. And
well, I would
the object is it's only it needs to be temporally restricted. Also. It won't work without that.
I would like to hear about it because, as I quote in Frege's Der Gedanke, he talked about the proposition cannot be true at a time, but true eternally at a time or false eternally at a time. And well,
but because of compositionality, the truth that must come from the composition of the object with the concept, etc. So you have to have everything fixed.
Yeah. Well,
he has no way around that.
Okay, guys.
So he has no object, no problem.
Very interesting. But I really asked about.
Yeah.
Okay, so now with our last presentation of today, we presented Cameron Baquero. He's from Universidad Conrad Lorenz, and he's a bachelor in mathematics. And we will be talking about the method of necessity, possible mathematical worlds, and thinking calculators.
Good evening. Hi everyone in Colombia. I'm here to present you my project that I've been building these couple of weeks. This is kind of new for me. I've been working with this with my teacher, Ruth Alejandra Torres. She's helping me. So what's this? It's something I've been building about how to create mathematics outside of mathematics. We call this meta-mathematics. Why? This is kind of a thing of study outside of the media, but using the same stuff we're working on. Sounds weird, but it isn't when we think about it. When we think about it, let's just say it. First, to understand this, let's go for what is ontology. Maybe you here know more about ontology than me, but ontology is just a study of the being of the objects, what kind of objects exist, the properties of the objects, right? And what interaction they have with each other. So here, we're gonna extend this to mathematical ontology, that is what kind of objects exist exist in mathematics, and what are the properties of these objects. And the funny thing about this is that we have a lot of things that we have to talk, because in mathematics we have dependence, fictions, and necessity with each object. For example, when we talk about ontological dependence in mathematics, we have to talk about worth. A mathematical worth is a snapshot of reality where something exists only in worth. I'm going to be in more detail next, but here I want to explain you that, for example, natural numbers only exist in the base, but if we have integers, it has to be a base for that, so we have natural numbers to cover that space. If we need to build rationals, we have to have integers, and that's like that. A word is sustaining the other, and that's it. It's easy to understand. There is also groups and rings and fields that is also have this property that one sustain the other. This is a dependence is one after the other. One can exist if the base is not real. For example, if you build in this building, we have to start with the base. There's no other way to start. Now, what's a fiction? I was talking about snapshots of reality. Those snapshots of reality are a fiction. Every fiction is contained in its own universe. Those universes contain some truths that are only for that place. For example, we have piano absolutization that has set axioms, for example, that allow us to build all natural numbers, starting with 0 on the sequence, 0 plus is a number, the next one. Or we have set theory, and we have anything else that is building. We have all those fictions contained in a different fiction. We can go from fiction to fiction by bridges that complement each other. Doesn't mean that they are existing in those fictions, but there are bridges that contain each fiction, one to the other. But they're like these kind of movies. When you go to the movies, there's like fiction, and you can just think about reality and compare that, because it's fiction. They have their own set of rules. Same with mathematics. And now, let's go with ontological necessity. That's the last part I want to explain before I go with what I want to do. Ontological necessity is kind of particularly alike what we expect with dependence, but here it's just with one word. We have one word, and we have to look at what makes the word work, what the main axioms, like the tree. We need to have the base of going to the branches, that will be the theorems we build after that. This is kind of important after, so what I'm gonna build. So after having these concepts, we're gonna move it's gonna be different. But right now I'm gonna move just to modal logic. Modal logic is an extension of logic that has two new operators, that is necessity and possibility. Those expressed by square and a diamond. So nothing more about this, but this is the following rule that we need to know before we go anywhere else. That's what it's explained about. We have P, and this is necessity P, or possibility P, and we have the negation of that. And I'm working with system K, or if you want to talk about relations in this, it's going to be no transitivity in this one. We have distribution, modus ponens, and that's it. This is the rule. I'm setting the model for what I'm going to do next. I'm now moving again. It's so weird, but I keep moving. But it's gonna be all be worth at the end. Cryptic semantics. What's cryptic semantics? There are two things of cryptic. There's cryptic models and cryptic structures. Models are a structure that are more for a computing system. For analyze, we have structure, we have a set of relationships, and we have a function that says that works or not. Same with scripted model, but what a model does is just having a set of words, having a set of relationships between those words, and rules that say what's true or what's not in those words. So, before that, going back here, I'm going to do this that, for example, for a cryptic model, we have 3 elements. Those are a set of words, a relationship, a binary relationship, and a function. We say that, for example, for a given word, let it be W, that has W1, W2, to Wn, let be Wn any natural number, set of words with their own rules. We say that we have a function B, and let it be a function B. The function B is, here. Let it be a relationship between this and a proposition. This is gonna give me a Boolean answer between 0 and 1, that be true or false, or we can call it true or false, if false true. And what we're going to do is, with this function, just introduce our given word, let be Wi, and our proposition. So what I'm going to receive here is either 1 or 2, either 1 or 0. This is going to say what is true or what's not in every natural reality we have in this universe of words. And now we have a binary relationship that what it does is just giving us as contained until the between two words. It's just this. We have a function that for this we take any given word, for example, give I that is contained in this set, and Wi, Wj. What we're gonna have here is we're gonna have here is Wi axis, W axis, Wj. Thus, when you have this, you're gonna have all the propositions that is true in this word and true in this word to set a relationship. If both are true, for example, we have a given P, true in both words, we're gonna say it's a necessary proposition. But if it's only, for example, in this word it's only P2, it's only true, then we say it's just possibility that exists because it's not for every word. So we're gonna see that here with all the properties it has. Let's say we have an M model where we say W simplifies P. If P, if in a given function, P is a true function in that word, we say that W doesn't satisfy a given phi, a formula phi, if this is not true in the given function. And same with this conjunction. If phi and phi are both true in that given word, then it has to be each one true. And for being necessary, let's build a W prime here in the W prime here in W, like the same here about W, containing in the W, we say with the relationship, it has to be that W is both true in W and W prime. Say something similar goes here, where W prime is just real in W prime that contains W. In the relationship, it's just true in one of the words, so it's not containing all of the words we have. So, from structure to model, this is kind of interesting because we can think this whole abstract thing that I'm saying right now doesn't seem like having a connection, but we are going there. What happens? If we have a word, this set of words have all of those propositions that we have here, and we can put all in a node that it has all the properties, P, Q, R, etc. And we call this node. This node is going to be connected to any other word by a relationship. And we're going to give everything away, even this and this, the edge can have a weight. We have W2, W1, W0. And what's going to happen is that every true that is true in both words is going to be necessarily true. And if one of the words is going to be it's just true in one of the words, it's going to be possible true. That's kind of easy to understand right now. We're going to move it even forward. Map of necessity. If we have the given graph like this, we can start building not only like a set of just abstract words contained with each other, like just 50 applying, but with mathematical words. We have mathematical, then we have not only proposition but axioms that only apply for this word. For example, maybe I'll skip this, but we have geometry. In geometry, there are rules. For example, for plane geometry, we have 5 rules that are all as you can say for this. If we cancel the five axiom of geometry, we're going to have non-Euclidean geometry. For example, we're going to have spherical hyperbolic. You're going to have infinite parallels or no parallel at all. But if you cancel the second axiom of those, you're going to have anything geometry, and you could say, I don't remember what's the order of that, but you're going to have Poincaré projection geometry if you cancel other axioms. That's why some of the word has all the rules, but none of the rules are true in all the words. For example, this word can be just the 5 Euclides with the 5 Euclidean axioms with here, but some of them, all of them can be true. Then we have the classical like this, just plain geometry. But if one of the other words we have here, for example, we don't have the fifth one, we're going to have 2 new geometries based on that. Why I'm telling you this? Because what I want to build here, what I'm going to build here is a way to, based on computing science and logic, building a way to make a child work. Let's be this two set of words. And what I'm going to do is build a child based on this word. This child is going to inherit all the necessary truths for both of the words. Let's see, there's a child over here. It's going to be inherit all the. I'm going to define a function that's called a W. That is based on these functions. Like we have all the truths in each word. We have all what is necessary for each word. So what is necessary is going to be always be in the child. And at last, I'm going to define a fifth. That's going to be a combinatory. All the possible truths are going to be combined in different kind of ways. For example, this child going to have some of the necessary. Let's see, P5. It's going to be true. But I'm not going to build one child. I'm going to build as much as I can do, but combining all the possible truths that is in each word. So I'm going to have a whole word with P5 is not available and a P5 word is true. And what's going to happen here is interesting. We're going to build mathematical words that are going to be contradictory. Most of them are not going to work because those truths are kind of messed up and define the word and maybe fall down. But some of them are going to work. So I'm making more questions than answers here. Why? Because what I want to do is build more fields of mathematics based on this. When I fill a model, all the information I want to get about each word and word 2 and building child word based on them, and this function G that contains all the functions that is just each set, but I'm gonna just build this in order to create new mathematics based on those words. So when I happen this is people go into mathematics. This is kind of more uninteresting thing. When people go to mathematics, go like this. You just take a problem and they just zoom in this area, zoom in all the possible that can be, and understand mathematics like that. Is over-specialization. Mathematics is based on over-specialization. What I'm doing is the opposite, going zoom out, and instead of creating and proving axioms, what I'm doing is going out and looking for those words that are ignored because we over-specialize in each word. So what is necessary for a word can be for other, and this is more generative, so I'm going to do it by computer. So because if I do it myself, it's going to take years maybe, because the complexity is going to be a lot. So for example, if you ever seen this image, do you know this? See it? Yeah? Okay. This is a famous that someone built long ago in 2017 about what fields of mathematics there are there. So this is kind of interesting. You can see a lot of them. And this is one I found in GitHub when I was researching for my works. They are doing this manually. This is not a graph that has anything to do. Just do it like, oh, I'm gonna put this because it fits. It's not like they have anything to do. They just study the word and do it just by hand. So I'm gonna ask you all here, how many fields of mathematics do you think there are right now?
Let's say k into power n.
I mean, it depends on the
Give me a
granularity. It depends on the granularity, but
Yeah.
it's in the hundreds, I guess.
Anyone say more, less?
I always remember the essence of mathematics is its complete freedom.
Yes.
Yeah.
So
Create the
1,000.
time and
1,000. Someone say less, more?
1,000?
1,000. Sell by 1,000. Everyone 1,000. Okay.
Is there money on the
Too
table
much.
for this?
Yeah. Yes. 1,000. Just 1,000. Okay. I'm going to stick with 1,000. There's 6,022
Okay.
possible mathematics only in 2020. Is this is having end? So maybe by the end of this decade, it's gonna be more. Just see at this. This is what they count as categories of mathematics in sub areas. They have this. Yes, they do that. And what I'm looking for is building all more mathematics, but I'm not gonna be focusing on those. Just in zooming out and seeing all the mathematics that exist. So what I'm doing for this is making a thinking calculator. A thinking calculator is kind of AI, kind of these things. We, instead of asking what's 2 plus 2, we asking what's the meaning of each thing. Is generative logic, this logic that generates itself. So we have, before we have samples, we have, when I say I create a model with information by myself, I have to do it. And a second model in the first phase. In the second phase, it's going to do it by itself, trying to create the words like using combinatorials to see what's going on there. Right now, it's kind of basic level what I'm doing. I have this model I've been building in my computer that has this managed word, analyze, simple.
Can someone back there turn off the lights, please? The last screen. The bottom. Thank you.
Okay, so it's pretty simple. You select a word, you analyze statements. That's the funny thing. Analyze statements is my favorite one. You go and ask anything. If it's necessary, is it works, is not. So I fit with this. Right now I'm building these ones with Serena Flanco, piano semanticization, and classical logic. And we have Olama API that was easy to get. And for now I'm using that because it's not quite yet my local ML. I call my machine learning model, but it haven't been working well right now. So when I ask in anything, for example, maybe as a statement in classical logic, and say that is the log split, is necessary current context, minimal recurrence, just the 1 to that word, so it's necessary. And here it's a negative numbers, and but we can natural numbers. It's possible we can have negative numbers because 0 is the one that doesn't have a successor. Then we can have natural numbers in piano semanticization. This is words that we will build it, giving it all the information necessary in order to work. Right now, this. What's next is putting modal logic here to building this. And then it's analyzing this by using the same model that here I have, analyze statements, in order to see if it works or if it's failing. So that's what I've been doing all this time, and that was my future reaction. What I'm gonna do, I explained you already good. So, I forgot the visual word explorer. That's gonna also be the same as here. I want it to be like this. If it had a bigger weight, it's gonna be a bigger edge. So I want to build this so we can zoom in and more spectacle than anything else, but it's actually, I like it, so I want to be like this. Okay. It's actually all over, so, oh, great. Conclusions. And let's go.
Thank you very much, Cameron. So, questions?
Well, I'd like to know better what the large language model is doing.
The large language model?
Yeah, just the machine learning models.
Oh, but right now it's just giving you, well, you building a local model. There's no local model. And it asks you for giving the statements. You give it statements.
But like natural language.
Yes, statements, because it has natural language in order to work. And the Olama thing is easy because it's just AI, and you just have to play the API. I'm trying to build myself one. So have all the things I don't want to be there to be explored.
So like you give it a natural language sentence.
Yes. You can say hello, but it's gonna say nothing.
And what does it do? What does it try to answer?
Well, it's gonna answer this. For example, I say this, it gives you word status, the axioms that you have, and it's gonna say you, in the current concept, minimal axioms. It's simple. How many axioms you need to build this, or if it's possible or not.
Like it performs a search over known axiomatic systems?
Yes, over the specific system you're building in. For example, I gave all the information about the system, all the information about this one, and it's gonna search in that information to do if it's possible or not. Why aren't you asking?
And the search that it does, does it use an external tool, like one of the like the verifiers and so on? Or is it reasoning using its neural network, which is approximate?
Yeah, just approximate right now. It's not verifying, so it's just doing best to work.
Okay.
Brandon has one.
Oh yeah, no, I like the idea of this is kind of an exploratory project, you know. That's an area where machine learning is really cool. Like exploratory data analysis is a huge thing. So but this is interesting because it's not, in mathematics, in experimental mathematics, often people just look for conjectures or something like that. But you're looking for new mathematical worlds entirely, right? Not just individual statements. That's pretty cool.
Yeah, I mean, and hallucinations are very nice too. I'm not kidding. Right? The large language models are hallucinating and suggesting new theories. Some of them are crazy.
Yes.
And some of them are not.
Right.
Yes. Maybe I'm taking part of the fun of it because people like to find this word that is more accidental. Yeah. But I'm making the word for them like, oh look, you want to study more mathematics? There's that thing that no one has ever done.
Yeah. That's an idea.
Okay. Anyone else? Philip?
Yeah. I don't know if this is relevant to you or not, but I'm familiar with David Hankey's work on his multiverse of set theories, and particularly his idea of working with modal logic in set theory using forcing as a accessibility relation to.
Joel Hampton?
Yeah, Joel Hampton.
Yeah.
Well,
are you familiar with?
No, not very much. I'm just starting. Yeah.
Yeah. Okay, so he has some ideas that I think maybe relevant to you.
Definitely.
Anyone else? Okay.
I'm just trying to understand better what's going on. Like there's two different things I think your system is doing. The first one is verifying among the existent models what are the minimally required axioms.
Yeah.
But then there's also the discovery part.
Yeah, but
something
it
else
hasn't been done. Don't worry about it.
Oh.
This part is just in progress.
There's no slide for it. It's
just no slide for this. Just I'm gonna do it in the future.
Okay.
Okay, so that's all. Thank you, Cameron.